In second quantization, we have started to deal with the problem of quantization of Schrodinger field in the previous lecture. In the first part of the lecture on quantization of Schrodinger field, we have seen the basic concept of the second quantization of Schrodinger field. And as I have told you in that lecture that for convenience we have to divide this lecture in three parts. The first part of this lecture you have already attended. Now the remaining two parts of the lecture on quantization of Schrodinger field we will actually see now. This is today is actually the second part of the lecture on quantization of Schrodinger field, in which we are going to discuss the problem of system of bosons, and finally in third part we will see the problem of system of fermions. Okay. So let us start to deal with the problem of system of bosons regarding the quantization of Schrodinger field. When you say quantization, that means second quantization. Okay. In fact, this lecture is somewhat lengthy, so it will take time, and after that when we will attend the lecture on system of fermions, that will be a short lecture, because several things which we have to know to deal with this problem we will learn in this lecture. So this lecture will be some time taking, some lengthy, but when you will attend the complete lecture, definitely you will feel very easy to understand the problem of system of fermions. Okay. As you know, bosons are the particles which obey actually the Bose-Einstein statistics. In my lectures on Bose-Einstein statistics, you have learnt about the bosons, and so I hope you have an idea of the physics of bosons. Okay. You know that this particle boson has actually either zero spin or integral spin. When you say integral spins, it means the spins of this particle boson must be either 0 or h bar or 2h bar or 3h bar and so on. Okay. And as I have told you that these particles obey the Bose-Einstein statistics, and you have learnt in the course on quantum mechanics that these bosons do not obey the Pauli's exclusion principle, as these have actually symmetric wave function. And when you say that the bosons do not obey Pauli's exclusion principle, what does it mean? It means any number of bosons may be in the same quantum state. Okay. So to deal with the problem of quantization of this Schrodinger field regarding this system of bosons, actually we have to adopt the condition or the idea which was actually developed by two famous mathematicians, and those were actually Jordan and Klein. Okay. And regarding this we consider two operators. The first operator I have considered is ak hat, and another is ak hat dagger. Actually this ak hat dagger, as the symbol represents, this is just the Hermitian conjugate of the operator ak hat. Okay. And these two Hermitian operators ak and ak hat dagger actually obey the following commutations rules, and these commutations rules read like this. This is commutator of ak and al dagger. This is equal to Kronecker delta kl. So it means when k is equal to L, then this commutator will be equal to 1, and if k is not equal to L, then this commutator will be 0. And At the same time, these operators also obey the commutation rules like this, that commutator of ak hat and al hat, okay, that is equal to 0. And similarly, the commutator of ak hat dagger and al hat dagger is also equal to 0. Actually here, these two operators, ak hat and al hat, refer to the same time t, okay. And for dealing with this problem, now let us consider a Hermitian operator denoted by the symbol nk hat, and this is defined like this: nk hat is equal to ak hat dagger times ak hat, okay. We define this operator, okay. Now our aim is to write the eigenvalue equation for this operator nk hat, which has been defined in the manner as you can see in this equation 2. And for this, we consider that this phi k is a normalized eigenfunction, okay. So if phi k is the normalized eigenfunction, then you can write the eigenvalue equation for this operator nk hat like this: nk hat operated on phi k is equal to nk phi k. As you can see, this nk is actually the eigenvalue of this operator nk hat, okay. And equivalently, you can write this equation which I have mentioned here in this way. In the ket symbol, you can write nk hat ket k equal to nk ket k. Actually, this ket k represents the kth quantum state or kth eigenvector, which is actually phi k. In the ket symbol, instead of phi k, you can write only ket k, okay. You are aware with this notation because you have learned the mathematical basis of the quantum mechanics in my earlier lecture, okay. Now let us multiply this equation number 3 from left side by this bra k, okay. So multiplying by bra k from left side this equation 3, our result will be what? This will be bra k nk hat ket k, and that will be equal to what? In RHS you can see this will be nk, a scalar product of k with k, okay. But as you know that this nk hat we have defined in equation 2, and this operator nk hat like this. This is ak hat bar, sorry, ak hat dagger times ak hat, and as this k, or you can say this is phi k, is a normalized eigenfunction. So the scalar product of this k with k, which is equivalently written as integral of phi k star phi k d tau, this will be equal to 1. So instead of this scalar product of k with k, I have written 1. So in RHS there is only nk, okay. Now this LHS you can see can be written like this. This can be written as bra k ak hat ket ak hat k, okay, and that will be equal to nk, okay. Actually when you will write this operator ak hat dagger in at the place of bra vector, then this dagger should be not written, because at the place of bra vector this is already the complex conjugate, or you can say the Hermitian conjugate of ak, okay. And so this RHS you can see this is just equal to the square of the norm or the modulus of the operator a of ak hat k, okay. And since it is a square of mod of this much, so definitely the value of this nk, which is the eigenvalue of the operator nk hat, that must be greater or equal to 0. Its norm will be never in fact negative. Okay, so nk hat so nk is greater or equal to 0. In fact this nk has integral value starting from 0 to infinity at the step of 1. We will see it some time later. Okay, now we operate the operator ak hat dagger from left on the equation 3. You can see this equation 3 here. This is your equation number 3, and as I have told you that you have to operate the operator in fact ak hat dagger from left side on this equation 3. So after operating that operator, what will be our result? You can see this is ak hat dagger operated on nk hat phi k, and that will be equal to nk. Since nk is just a number, so it is outside of the operator, and ak hat dagger phi k. Okay, now the property of these two operators we have seen in first equation due to Jordan and Klein, that the commutator of this ak hat and ak hat dagger will be equal to 1, because you can see I have told you earlier here that when k will be equal to L, then this Kronecker delta will be equal to 1. So if you replace this L by k, it means you are taking k equal to L. Then in RHS at the place of Kronecker delta, you have to write 1. So this commutator of ak hat with ak hat dagger, this will be equal to 1. Now this commutator is can be written like this. This is actually just the definition of commutator, and page has been turned, but this will be just okay, so don't be worried. So let us see. This is equal to ak hat dagger minus ak hat dagger ak hat equal to 1. Okay, now I will not pronounce hat, only I will read ak and ak dagger, but you have to see that this is ak hat. Okay, so from here you can see that this ak dagger ak will be equal to ak dagger minus 1. Okay, but as we have defined this number operator nk hat like this, this is ak dagger ak. So instead of this ak dagger ak, I have written here nk hat. Okay, and that is equal to ak dagger minus 1. Okay, so substituting this expression for nk hat in this equation number 5, what will be our result? You can see in the LHS of equation 5 there is ak dagger, so I have written here ak dagger, and instead of this nk hat we will write ak dagger minus 1, and this is operated on phi k, and that is equal to nk this much. So this is nk ak dagger phi k. Okay, now we will simplify the LHS of this equation, and you can see what will be this. The LHS will be ak dagger ak dagger minus ak dagger phi k equal to nk ak dagger phi k. RHS is at each. Okay, and the first term in LHS you can write this will be ak dagger ak operated on ak dagger phi k, and let us take the second term in RHS, and when you will bring the second term in RHS, the RHS will become nk plus 1 ak dagger phi k. Okay, ak dagger phi. But again you can see that this ak dagger ak, you have assumed that this is equal to nk, so instead of this I have written nk hat. Okay, and this ak dagger phi k is at each, and RHS is also at each. Okay, So now you can see that when you have written the eigenvalue equation for this nk hat operated on phi k, your result was nk hat phi k equal to nk phi k, and you have told that uh, for the operator nk hat, when the eigen function is phi k, then its eigenvalue is this nk. Okay. Similarly, you can see this equation 6 is nothing. This is simply the eigenvalue equation of this operator nk hat 2. Okay. In fact, here the eigenvector is not phi k, but eigenvector is ak hat ak dagger phi k. But when the eigenfunction is ak dagger phi k, then the eigenvalue of the operator nk hat is not nk, but its eigenvalue is nk plus 1. So this ak dagger phi k can also be assumed as an eigenvector or eigenfunction for the operator nk hat when its eigenvalue will be equal to nk plus 1. Okay. And in the similar manner, if you consider that ak phi k is the eigenfunction of this operator nk hat, then in the same manner you can work out the algebra and you will get that the eigenvalue equation will become this much: nk hat operated on ak phi k, that will be equal to nk minus 1 ak phi k. So you can say that this ak phi k is also an eigenvector, and when it is it will be the eigenvector of the operator nk hat, then the eigenvalue of this operator nk hat will be nk minus 1. Okay. So actually till now you have considered three eigenvectors. When eigenvector is phi k, then the eigenvalue of operator nk hat is nk. When the eigenfunction is ak dagger phi k, then the eigenvalue of the same operator nk hat is nk plus 1. But when the eigenvector is ak phi k, then the eigenvalue of the operator nk hat is nk minus 1. Okay, nk minus 1. So this result shows that as I have told you that ak phi k is also an eigenfunction of the operator nk hat having the eigenvalue nk minus 1. Okay, I think you are getting the things. Now you can see that in this case the operator ak dagger increases the eigenvalue of nk hat by 1. On the other hand, this operator ak decreases the eigenvalue of the operator nk hat by 1. Just you have seen this. And this is the reason that we simply say this operator ak dagger as a creation operator, because it increases the eigenvalue by 1. And this operator ak hat decreases the eigenvalue of nk hat by 1. So this is called annihilation operator. Okay. Or in other words, you can also say that this ak dagger is raising operator and this ak is lowering operator, because ak hat raises the eigenvalue by 1 and ak actually lowers the eigenvalue by 1. Okay. So these are also called raising operator and lowering operator respectively. Okay. Now the eigenvalue spectrum of the Hermitian operator nk hat, as I have told you earlier, the nk hat which is defined like this, are actually non-negative integers. I have told you earlier that this nk hat is simply equal to these positive integers at a step of 1. This is equal to 0, 1, 2, 3 up to plus infinity. Okay. And this is the cause that we simply say that this nk is nothing, this is a number operator. And as it is a number operator, so it must satisfy this commutation relation, that is commutator of nk hat and nl hat must be equal to 0. Okay, and actually when this commutation relation holds, that actually shows that the set of number of operators can be diagonalized simultaneously. Okay, it is clear from this result. Okay, actually this set of Hermitian operators form a complete set which spans all the Hilbert space. You have actually studied this fact while the study of Hilbert space in my earlier lectures. Okay. Now let us consider that this set has eigenvalues like n1, n2, so on, nk, and so on. And so that one such eigenfunction can be written like this. This is phi n1, n2, so on, nk, so on. And that is equal to ket n1, n2, so on, nk, so on. Okay. Actually, the most general eigenfunction psi you can obtain simply by the linear superposition of these eigenfunctions. Okay, and the eigenfunction for which this nk is equal to 0, that eigenfunction is called ground state eigenfunction, or it is also called vacuum state function. Okay, so remember this. The eigenfunction for which nk is equal to 0, that is called ground state function or the vacuum function, or vacuum state function. Okay. Actually, in terms of this vacuum function, which we will denote by the symbol phi naught, or you can also write it like ket 0, we can actually generate the function like phi n1, n2, so on, nk, by the repeated application of the operators like ak dagger. By the repeated application of this ak dagger, you can generate the function like phi n1, n2, so on, nk, and so on. Okay, and how we can generate such functions, you can see this is phi n1, n2, so on, nk, that can be written as C, where C is actually normalization factor, a1 dagger to the power n times a2 dagger to the power n, so on, ak dagger to the power nk, so on, phi naught. Okay, or in ket symbol you can also write this state can be written in ket symbol like this, ket of n1, n2, so on, nk, and that is equal to C a1 dagger to the power n1 times a2 dagger to the power n2, so on, ak dagger to the power nk, ket 0. Okay, and as I have told you that this c is nothing, this is simply the normalization constant or normalization factor. Okay, actually in an alternative manner, this result can be written like this: ak dagger operated on this eigenvector ket n1, n2, so on, nk is equal to alpha of nk and ket n1, n2, so on, nk plus 1, so on. Because here the operator is ak dagger, and you have learned that this is a creation operator or the raising operator. It increases the eigenvalue by 1. So I have written here nk plus 1. Okay. And in the similar manner, you can write ak hat operated on ket n1, n2, so on, nk is equal to beta of nk, ket n1, n2, so on, nk minus 1, so on. Okay. Actually, this alpha of nk and beta of nk can be obtained by combining these two equations. So when we will combine these two equations, simply you can write ak dagger ak operated on n1, n2, so on, nk, and that will be equal to beta n of nk times alpha of nk minus 1 and ket n1, n2, so on, nk. Okay, or you can see that this ak dagger ak is equal to nk hat. Okay, So instead of this, I have written here nk hat, and this is operated on kate n1, n2, so on nk. And as you know that this nk hat, when will be operated on this eigenvector, this is just an eigenvalue equation, and its eigenvalue is equal to nk. So I have written here nk, and the eigenvector is kate n1, n2, so on nk. But you can see that here this nk has been written at the place of this beta of nk times alpha of nk minus 1. So you can equate this nk by this product of beta and alpha. So you can see this beta nk times alpha nk minus 1, this is equal to nk. And similarly, you can write that if nk will be replaced by nk plus 1, then this nk minus 1 will become nk, okay, and this nk will become nk plus 1. Okay. Now from these two equations we can easily find the value of alpha of nk and beta of nk. You can see, if our aim is to find alpha of nk, then in equation number 13, k will be replaced by k plus 1. K will be replaced by k plus 1. Then this alpha nk minus 1 will be alpha k, okay? And this beta nk, this will be beta nk plus 1, nk plus 1, okay? And in RHS, this nk will be nk plus 1, okay? And so in this condition, when you will multiply these two equations, there will be simply this will be alpha square, and that will be equal to nk plus 1. And so this alpha nk will be a square root of nk plus 1. And similarly, if your aim is to find beta nk, then you have to you have to put k instead of k plus 1 in this equation 14. And when we will replace k by k minus 1, then here will be beta nk, and alpha nk will be alpha nk minus 1, and nk plus 1 will be nk, okay? And so from here you can find that nk will be equal to root over nk. Beta nk will be root over nk. So in this way you can see we have obtained the value of alpha nk and beta nk, okay? And therefore we can write this result, that ak dagger to the power n1 times a2 dagger to the power n2, so on ak dagger to the power nk, kate 0, and that will be equal to a square root of n1 factorial times n2 factorial times nk factorial, and kate of n1, n2, so on nk, okay? Now we will compare this equation 16 with the equation number 11. So you can see this is your equation 11, okay? Here actually this kate n1, n2, so on nk is equal to this much, and we have defined this a1 dagger to the power n1, a2 dagger to the power n2, so on ak dagger to the power nk. We have defined. So when we will compare these two equations, you can see that this constant c, which is the normalization factor, this will come out to be 1 over a square root of n1 factorial times n2 factorial times nk factorial, okay? So in this way we can obtain the value of the normalization factor. after getting the value of this normalization factor, you can put the value of C in equation 11, and then you can write that equation in this manner. This is kth n1 n2 so on nk, and that is equal to 1 over a square root of n1 factorial times n2 factorial times nk factorial. Okay, and a1 dagger to the power n1, a2 dagger to the power n2 so on, ak dagger to the power nk, kth 0. Okay, this is actually kth 0 represents the ground state function. Okay, now in the similar manner, when we will do some algebra, you will get that in general ak to the power r times al dagger to the power n kth 0, this can be will be equal to n factorial divided by n minus r factorial ak dagger to the power n minus r kth 0 delta kl. Delta kl, this is Kronecker delta. And so that you can see that this result can be written as ak to the power n al dagger to the power n kth 0, this is n factorial delta kl kth 0. Okay, and actually when these results will be used, we can then find that that bra n1 hat, n2 hat, nk hat, and kth n1, n2, nk, actually this is the scalar product of this n1 prime, n2 prime, nk prime with a n1, n2, nk state. Okay, and that will be equal to delta n1, n1 dashed, delta n2, n2 dashed, so on, delta nk, nk dashed. This can be written. Okay, and in this manner you can see that this equation shows that the base vectors are orthonormal. Actually, this is the condition of orthonormality. You know that if the scalar product of two eigenvectors psi1 and psi2 is equal to delta 1 2, actually then you say that the eigenvectors are orthonormal, and so that equation 21 shows that the base vectors are orthonormal. Okay, actually these vectors constitute particle number representation for the operators ak hat, ak hat dagger, and nk hat, and you can write the eigenvalue equation in this manner, that ak dagger operated on kth n1, n2 so on nk equal to a square root of nk plus 1, because you have learnt that its eigenvalue is in fact alpha k, and that alpha k is equal to a square root of this much. Okay, and the same eigenvector n1, n2 so on nk plus 1. Okay, and when ak hat will be operated on this eigenvector n1, n2 so on nk, the result will be a square root of nk, n1, n2 so on nk minus 1. This is in fact nk minus 1. And when nk is operated on kth n1, n2 so on nk, that will be nk kth n1, n2 so on nk. Okay, and these results hold in such a manner that you can write that n1 dashed n2 bra n1 dashed n2 dashed nk dash and kth and nk and kth n1 n2 so on nk, and that is equal to nk delta n1 n1 dashed delta n2 n2 dashed delta nk nk dashed. Okay, actually this equation 23 which we have written here shows that nk hat are diagonal operators in this representation, that is in this number representation, these operators are diagonal operators, and with the diagonal matrix element nk. Okay. Now the quantum field which we are talking about is given by this operator, or actually this psi of rt equal to summation over k ak of t uk r. Actually this representation of psi has been discussed in the first part of the lecture, so you can remember this result. Okay. And this result holds when the scalar product of uk and ul, this is just equivalent to integral of uk star of r, this is complex conjugate of uk, and ul of r d tau equal to delta kl, and at the same time summation over k uk of r uk star of r, this is delta r minus r dash. Actually this delta r minus r dash, this is what? This is actually this delta kl, this is a Kronecker delta. Okay. And this delta r minus r dash, this is actually the Dirac delta function. Okay. Dirac delta function. And you know that this function is equal to 1 when this will be actually equal to infinity when r will be equal to r dashed. Okay. And this will be equal to 0 when r is not equal to r dashed. Okay. Now if you write the eigenvalue equation for a single particle, then the single particle Hamiltonian we denote by the symbol hp hat, and this will be operated on ukr, and that will be equal to epsilon k uk of r. Actually this epsilon k is the energy eigenvalue of a single particle. Actually this single particle Hamiltonian, you know, this is defined as minus h bar square over 2m del square plus v of r. Okay. And so if you want to write the expression for this Hamiltonian for the system of particle, not single particle, then this h will be equal to summation over k nk hat epsilon k. Okay. And so you can say that the eigenvalues of the Hamiltonian for the quantized field will be what? What will be the eigenvalue? You can see that this eigenvalue E will be equal to summation over k nk epsilon k. And for this the corresponding eigenvector is like this. This is k n1 n2 so on nk. Okay. Actually this result you can say that this shows that the matter field can be thought as an assembly of non-interacting individual particles, each of which has energy epsilon k, and this is actually this RHS actually represents the sum of the energy of all the particles. Okay. Actually the total number of particles in this system you can see can be written as n1 plus n2 plus so on nk and plus so on, and thus that can be written in brief like this. This is summation over k nk. Okay. And as you have obtained this eigenvalue of this system without any restriction on the distribution of particle in different quantum states, so you can easily say that there is no restriction on the number of particles in a particular quantum state. Okay. So you can say that any number of particles may be in any quantum state, and this is actually the basic feature of Bose-Einstein statistics, or you can say this is the basic feature of the bosons. Okay. And so you can say that this field actually represent the assembly or system of bosons. Okay. Now as nk is a number operator and this number operator actually commutes with the Hamiltonian H. And so you can write that this nk hat, the commutator of nk hat and h hat, can be written as summation over kl and epsilon l commutator of nk and nl, and that will be equal to 0. And actually this result implies that when potential function v does not depend on time, the total number of particles in the field is a constant of motion. Okay? And as I have told you earlier, that the operator ak dagger increases the particle number by 1, because now you have learned that nk represents the particle number, and ak decreases the particle number by 1. So in this because of this, we simply call this ak dagger as creation operator and ak as annihilation operator. Okay. So I think this was somewhat a lengthy lecture, but I hope you have understand the each and every step. Definitely watch the video seriously, write down these things in your notebook, and then revise it. After revising, everything will be clear to you. Okay? And in the next coming lecture on this quantization of Schrodinger field, we will see the system of fermions, and that will be a short lecture, because most of the aspect which needed to deal with the problem of system of fermions we have learnt in this lecture. Okay, so thank you very much.